Section 5.2 talks about the definite integral, and here's the deal. Let f of x be function defined on a to b. The definite integral of f of x from a to b is given by, so remember this Riemann sum limit, where this x sub I star could be anywhere in the interval, and that was a plus I times delta x, a being the starting point, and delta x is b minus a divided by n, provided this limit. So this equal this sum is at approximate area, but if I take the limit as n approaches infinity of this, that becomes this integral, the integral from a to b of f of x dx. Basically, f of x is pretty much that, and delta x is an approximation of that, provided the limit exists. If the limit exists, the function is said to be integrable on a to b, or is an integral function. Well, we just want to express that back and forth how this works, and just to kind of look ahead, this was approximating the area under the curve if the function was above the x-axis. If you take the limit as n approaches infinity, if you add an infinite amount of those rectangles, whether you use left or right, we're going to stick with the right. If you use right-hand approximation or left-hand approximation, but if you fit an infinite amount of rectangles under that function, then you're going to find the exact area. The heights are going to be infinitely close to each other so that there's no gap. In the following exercises express the limit as an integral. Well, that seems to be the easy direction, going from left to right, from right to left. But going the other way, which is the next, is going to take a bit of work because you need to find that. Well, here, so 1 to 3 of x sub I squared delta x. Well, that is x dx. And how do you know that? Well, what did they substitute x sub I star in to get f of x sub I star? Now, once you see the second, I should have started with the second example first. Let's talk about this problem. So here, this is going to be the integral from 0 to 1 of f of x sub I star. Well, let's see how this worked. They really took delta x is delta x. If you take x sub I star and you substitute it in f of x, you get the sine squared of 2 pi x sub I star. And according to this, all what you have to do is, this is simply f of x. So this is just f of x, which is x, and here, this is just the sine squared of 2 pi, that would have been a constant, the sine squared, oh come on, that would have been the sine squared of 2 pi x. So the only thing you're changing, you're switching the x sub I star to x, pretty much, and everything else you leave the same, and just write the interval from a to b. Here they're giving you that, and that's pretty much it. Now, in the following exercises, given the left or the right, actually I eliminated the left out of the equation. We're only doing right. As indicated, express this as the limit, express their limit as n approaches infinity as a definite integral. If I take the limit as n approaches infinity of 1 over n, the series I equal 1 to n of I over n, I want to write that as the integral. Well, I need to figure out a few things. I need to figure out a and b. That's the hard part. and f of x. Well, let's see. First, we start with delta x. Delta x is b minus a divided by n. And if you look closely, there's delta x. That is 1 over n. So that would be what? The ends match. That means b minus a is 1. The length of the interval is 1 unit. Now, I just need to know where does it start? And that's where this comes in. F of x sub I star. Well, f of x sub I star is pretty much I over n. And that should resemble the inside of it. So that's f of I. Well, we know what that is. That's pretty much delta x up there times I. So we know a plus I delta x should equal the I over n. But I times 1 over n. Delta x is right there. So that means we must have started at 0. So we know that a is 0. And if we know a is 0 and the length of the interval is 1, we know that's 1. And what's f of x? Well, f of x is just x dx. So what do you substitute? I over n to get I over n. You just substitute it in x, nothing more. Second example hopefully will make this a bit more clear. So let's start. We want delta x. Delta x is right there. Delta x is 2 over n, and that should be b minus a over n. So we know that b minus a is 2 units. We know b minus a is 2. In this case, you're running 2 units. We need to know the starting point. We know x sub I star is whatever you take in f of x with. Well, that's what? That's a plus I times delta x. In our case here, that's going to be a plus I times delta x, 2 over n. Well, if I glance at what I'm given 1 plus 2 times I over n. That means you're starting at 1. If you're starting at 1 and the length of the interval 2 units, so we're integrating from 1 to 3. And what do you substitute this in to get it back? Well, that's just x dx again. And if I wanted to make that more interesting, I would have made that, and I should have probably made that a square. There. If I would have made that a squared, then we would have said that's a squared. And if I look at the last third problem, I'm looking at, okay, delta x is b minus, of course, we're taking the limit as n approaches infinity of this as well to get, so the limit as n approaches infinity of this sum gives you that. And here we're doing the same. We're taking the limit as n approaches infinity of r sub n, of this mess, and that gives us the integral. And let's see, b minus a over n should be, it's right there, it's 2 pi over n. So that means b minus a is 2 pi. I know the length of the interval is 2 pi. I need to get the starting point. Well, x sub I, it seems, substituted there and there. X sub I star is a plus I times delta x. I times delta x we know is 2 pi over n. So if they say that equals 2 pi over ni, right? We know that they started at 0 and they went to 2 pi. So that's 0 to 2 pi. Now, what do you substitute this in to get that times the sine squared? Isn't that x, the sine, you square the x dx, and there it is. Now, let f of x be a function, an integrable function defined on ATB. Let a sub 1 represent the area between f of x and the x-axis that lies above the axis, and a2 represent the area between the x-axis below. Then the net signed area between x is given by those two. The total area is always given by the absolute value. Let me demonstrate really quick what's happening. It turns out this integral of f of x has one problem. Every time you integrate, the sum runs from the x-axis to the function. So if the graph is above the x-axis, like the examples we did in the previous problem, that's area. Here's the issue. Let's say that's 0, that's a, that's b. So from 0 to a, f of x dx will give you the first area. But if I run past a, it's going to run to the function again. An integral always starts from the x-axis. It's in terms of x. It runs from the x-axis to the function. Here it's going to be subtracting, but area is always positive. So if I really wanted to find this, since it's below the x-axis, I put a negative, and that's where the minus comes in. Dx, of course. And that will be area 2. So visually you have to look at that. And of course absolute value takes care of that, because absolute value will reflect the negative above, and it will find that area for you and eliminate all of that. But absolute value means you have to split it up. You have to look, where is it positive, where is it negative, and that's going to be the difference between area and displacement. And we'll talk about that in section 5.4. For now, let's focus on area. I forgot directions. Let me get directions. Okay, here's directions. In the following exercises, evaluate the integral of the functions graphed using the formula of area of triangles, circles, subtract the top and the bottom, and so on and so forth. Well, if we want to find the area of this, first we have to make sure that the function is always above the x-axis. It is in this case. That's going to be area sub 1, and that will be this area, plus a sub 2, that will be this area, plus a sub 3, and that will be this area. And you notice that the first is half a circle with a radius of 1. The second is also half a circle with a radius of, that's from 4 to 6, that's 2, and 1/2 pi times the radius squared. And here we're looking, let's see, 6 to 12. So what is that? 9. If I go from 9 to 6 or 9 to 12, that's 3 units. And that will be the exact area. That is pi over 2 plus 4 pi over 2 plus 9 pi divided by 2. So altogether, this area over 2, 9, 10, 14 pi over 2, or simply 7 pi. That would be it. Now here, we're saying this is an area because all of these are above the x-axis. When I get to this problem, I notice there's a negative. I say, okay, well, let's see what they want. Do they want an integral, or do they want the area? It says in the following exercises, evaluate the integrals. Now, an integral is simply the overall altogether between the positive and the negative. What's the outcome? So an integral could be negative, could be positive, could be 0. An area, if you have a function that's positive, an area will always be positive. In section 5.4, we're going to distinguish between those when we talk about find the displacement versus find the distance. So really quick, if I was standing at a point and I walked 1, 2, 3 units to the right and 1 unit to the left. So if I walked 3 to the right and 1 left. If I say integrate, assuming this is f of x, the integral of f of x will simply say 3 minus 1, 2 units. It'll say you are 2 units from where you started. If I say find the area, find the distance, this is displacement. If I say find the distance, you have to take the integral of absolute value of f of x, which is the area. It's going to say you moved 3 forward plus 1, so it's really plus the absolute value of -1. And it's going to say you moved a total of 4 units, 3 forward, 1 backwards. Now again, we're going to talk about that when we get to 5-4. For now, here they're saying integrate, take the integral from 0 to 12 of f of x dx. Well, that would be the first piece, it's going to be half the area of a circle. Now the second piece, since y is -2 and the base is 4, we're going to say it's going to be minus 1/2. Base is 4 units, the height is 2 units. And the minus comes from y being below the x-axis. And the third, of course, is from 9 to 12, that's 3 units. It's half pi times 3 squared. So that is pi over 2 plus 9 pi over 2 minus 4. That is 10 pi over 2, which is 5 pi minus 4. Now again, an integral, if this turns out to be positive, but if it's negative, an integral could be negative. Same deal here. If we look at those, we say, look, if we integrate from 0 to 12, this function f of x dx, it consists of 3 parts. First part is half a circle, it's positive. Second is negative, since this is below the x-axis, that's half pi times, and the radius here is 2. And here the radius is 3, half pi times 3 squared. So that turns out to be pi over 2 minus 4 pi over 2 plus 9 pi over 2. That 10 minus 6 pi over 2 are simply 3 pi. If you notice in the previous it was 7 pi. Oh, it's missing a lot. It was 7 pi, 9. Yeah. So now it's 3 pi because you're taking away the 4 pi over 2. Alright, and here in the following exercise, evaluate using, okay, again, it says evaluate the integral. The answer could be positive or negative. Well, how are we going to do this? We're going to graph these. Y equals 3 minus x, so you start at 3. You rise 1 down, 1 to the right. The line is infinite, but I am concentrating only from 0 to 3. There it is. And since it's always positive, we say this integral is 1/2 base times height. The base is, I didn't do this right. My line is way off. Rise 1 down. It should have been right there if I did this correctly. There. So we know the base is 3. And the height is 3. So that is 4.5 or 9/2. If there were units, I would have squared them. When I get to the next problem, 3 minus, so again I go up 1, 2, 3, and it crosses at 3 and -3. The absolute value looks like this. And if I want to integrate from -3 to 3, we're talking about this area. Again, it's all positive, so that's simply 1/2 base times height. The base, I'm running from -3 to 3, that's a total of 6 units. And the height is simply 3 units. and that's 9. And the following, we are already aware of this hopefully by now. This is half a circle with a radius, and again the upper half. They're talking about literally that region. And of course you're wondering, what if it's a geometric figure that you are not aware of a formula? Well, that's where the next section comes in. So half of 4 pi is 2 pi. And this is a circle with a radius of 6, shifted 6 units to the right. And if you don't see it, y equal the square root of 36 minus x minus 6 squared, square both sides. There it is. The center is 6, 0, and the radius is 6. So let's say 1, 2, 3, 4, 5, 6. There, we're talking about that right there. It doesn't matter whether it's shifted or not because the area doesn't change. That's 1/2 pi times the radius squared, and the radius is 6 in all directions. That's 36. Half of that is 18 pi. So those are quick if you could just figure out which graphs they're talking about. Now they're going to talk about some properties of integrals. Remember, those are summations. Whatever apply on summations, apply on those. And if we're talking about an integral, if you integrate, oh boy, shifting is annoying, very annoying in these cases. Okay. If you integrate, if you don't give it a width, then there is no rectangle and the area is 0. The integral from a to b is negative the integral from b to a. If you're taking the integral of two functions added, you could take the integral of each and add the result, same with the minus, just like we did with the summation. If there's a constant, you could drag the constant up front, integrate, and multiply the result by it. Here, it's a bit tricky. Let me show you really quick what they're saying here. And this is a massive deal. If I am integrating from A to B, if I'm talking about, and for simplicity, I'm assuming it's positive, if you pick a point C in there, then the integral from A to B, which is the yellow, would equal the integral from A to C plus the integral from C to B. So again, now let's just apply some of that, a bit of it, not that heavy stuff, just to make sure, just like we did with C summations. Suppose we have 4 integrals, 0 to 4 of f of x, 0 to 2 of f of x, 0 to 4 g of x, 0 to 2 of g of x. If I want to figure out this integral, well, according to the rule, I could do each of those individually and add the result. Now, if I glance at those, and in this case, it seems I'm using 0 to 4 specifically and 0 to 4 of g of x. One of them is a 5 and the other one is a -3. The overall is a 2. That's simple. Again, just making sure that we know how to use those rules properly. And here, if I'm dealing with a minus, I'll say, look, that is the integral 0 to 2 of 3 times f of x dx minus the integral from 0 to 2 of 4 g of x dx. we'll say that's 3 times the integral 0 to 2 of f of x dx, and here we can drag the constant up front. And basically that's simple. Simply looking at, we know that, oh, I marked the wrong one, didn't I? I should look more careful about the color, come on. And that's not a negative 3, that's my mistake. That was the green. 0 to 4 is right there. That's a negative 1. I thought they put F and G. I was mistaken. They put F first and G for after. So here when I'm looking at F from 0 to 2, F from 0 to 2 would be the blue. And G from 0 to 2 would be the pink. So in this case, we're looking at the blue is a negative 3 and the pink is a 2. So negative 9 minus 8, my answer would be a negative 17. And that's pretty much the idea behind this section.